Hi, today we will be talking about using Newton's second law in a different way than we have in the past two videos in order to quantitatively describe an orbit around a black hole. Earlier we have used Newton's second law to predict motion after having known forces acting on an object. Now we know the motion of the object and we are predicting the net force from that motion. In this lab, we are given the x and y coordinates of the star as it revolves around a black hole. To simplify things, we are assuming that the net force on the star is only due to the gravitational force from the black hole. The motion here is circular, so we must consider the parallel and perpendicular components of the star's momentum as it revolves around the black hole. Doing this allows us to predict a net force and therefore a mass for the black hole. The result here gained was that the mass of the black hole was equal to 3.9802 times 10 to the 31st kilograms and was located at that given position vector. Now we're going to take a look at the physics formulas we will use in this lab. First of all, we'll use the momentum principles, which is stating that F net is equal to dp dt, which is also equal to the parallel components of the F net added to the perpendicular components of F net. Similarly, dp dt is equal to the parallel components of dp dt plus the perpendicular component of dp dt. We will also be using Newton's gravitational law, which states that the gravitational force is equal to negative g, which is a constant, times the mass of the star times the mass of the black hole, all divided by the magnitude of r squared. Now let's go to Python, where we will implement these codes. First, let's take a look at the initializations. Here I've initialized a vector origin, which was given for the black hole. I've also have the star mass is 1.989 times 10 to the 30th kilograms and a delta t of 86,400 seconds, which is equivalent to 1 day. Next, let's take a look at the while loop, the first while loop. In this part of the code, the program will loop through the given CSV file of x and y coordinates to calculate an initial and final velocity for each data entry until it reaches the end. These velocities are then placed in the next while loop to calculate initial and final momentum from the velocities by multiplying that by the star's mass. Once we have obtained initial and final momentums and velocities, we can subtract the final minus the initial to obtain delta v and a delta p. Next, we look to solve dp dt. Here, dp dt is equal to the delta p divided by delta t, and the F net is equal to dp dt, which we have seen from Newton's laws. Next, we are calculating a unit vector, p hat, which is equal to the initial momentum divided by the magnitude of the initial momentum. Here, the magnitude of dp dt is equal to the magnitude of p final minus the magnitude of p initial divided by delta t. And now we are calculating the parallel component of dp dt, which is equal to the unit vector p hat times the magnitude of dp dt. Next, we calculate the F net of the parallel component, which is just equal to dp dt parallel. dp dt perpendicular is equal to dp dt minus dp dt parallel, as we have seen that the vector dp dt is equal to dp dt perpendicular plus dp dt parallel. And the F net perpendicular is just equal to dp dt perpendicular. As we end this code, I have asked it to print a formula which is basically saying, which is derived from Newton's gravitational law, which is calculating the mass of the black hole in terms of the magnitude of the net force, which we have just assumed is the force due to the gravity of the black hole, times the magnitude of the start position minus the origin position, or just r, magnitude of that squared, divided by g, and this is the g constant, times the mass of the star. As I run this code, you can see the force vectors as they change when they come in closer to the black hole. Here, the black arrow is equal to dp/dt parallel, the blue arrow is equal to dp/dt perpendicular, and the yellow arrow is equal to Fnet. As you can see, I have calculated the mass of the black hole to be 3.9802 times 10 to the 31st, which I have stated in the introduction. Now let's enter the discussion questions. For the what does it mean, the question is how are Fnet, Fnet perpendicular, and Fnet parallel different from dp/dt, dp/dt perpendicular, and dp/dt parallel? The answer to that is that although Fnet is equal to dp/dt in terms of the momentum principle, the two values signify different things. dp/dt is a value that can be calculated from the observed position data, as it was in this lab. Fnet causes this observed motion, but cannot be calculated directly from the position data. It is determined through dp/dt. The next discussion question is the what if. If the black hole was replaced with a new one, but the motion of the observed star remained the same, and is only affected by the gravitational force, could a new mass be calculated? In this case, no, because the revolving path of the star stays the same, and the values for dp/dt would also stay the same. Since dp/dt quantitatively describes Fnet, a new mass would not be able to be calculated through Newton's gravitational law. In conclusion, using dp/dt is a powerful tool in determining the net force acting on an object, especially when we only know the position data. dp/dt is able to quantitatively describe how Fnet affects the motion of an object, as we have seen in this lab. Thank you.